Welcome to today's paper reading. Today's paper is titled, Oryx MLLM, On-Demand Spatial-Temporal Understanding at Arbitrary Resolution. This paper was published on AR14 by Ziyan Liu and colleagues from Tsinghua University and Tencent. The abstract highlights the diversity of visual data, ranging from small icons to long videos. Existing multimodal large language models, LLMs, typically standardize these inputs to a fixed resolution, which is inefficient for processing both long and short visual content. To address this, the authors propose Oryx, a unified multimodal architecture designed for spatial-temporal understanding of various visual inputs. Oryx introduces two core innovations: a pre-trained Oryx ViT model that can encode images at any resolution into LLM-friendly visual representations, and a dynamic compressor module that supports variable compression rates. These features allow Oryx to efficiently process visual inputs of arbitrary sizes while maintaining high recognition precision, particularly for tasks requiring native resolution. Multimodal large language models, MLLMs, are advanced systems capable of processing both visual and linguistic inputs to produce coherent and contextually relevant responses. Proprietary models like those from OpenAI and Gemini teams showcase the cutting-edge capabilities of MLLMs. Meanwhile, the open-source community is actively enhancing MLLMs to better understand diverse visual content, including images, videos, and 3D data. As MLLMs become more powerful, there is an increasing need for more general and unified MLLMs that can handle a wider variety of visual content and more challenging multimodal understanding problems. Figure 1 illustrates the concept of on-demand multimodal understanding, highlighting how different visual data and tasks necessitate different input resolutions and compression ratios on visual tokens. This approach allows for a more general and effective solution for visual understanding within multimodal large language models, MLLMs. By supporting arbitrary resolution inputs in an on-demand manner, this method addresses the specific needs of various tasks, such as text retrieval, object recognition, and frame localization, ensuring optimal efficiency and performance. In the realm of visual encoding for multimodal large language models, LLMs, previous works have employed various techniques. Oryx et al., 2022, and Li et al., 2023, used attention mechanisms to capture visual features, while Liu et al., 2024 D.B.F., opted for a simpler MLP approach. High-resolution perception has been advanced through dynamic partitioning, though it is inefficient and may lose critical information. On the multimodal LLMs front, recent models like 3D-LLM, Hong et al., 2023, have expanded comprehension to 3D environments. However, these models often face limitations such as fixed resolutions and reliance on enhanced data curation. This paper aims to address these challenges with a novel framework. The Oryx model introduces a novel architecture designed to handle visual inputs at their native resolution, which is crucial for maintaining the integrity of visual content. This is achieved through the Oryx ViT, which uses variable-length self-attention to process visual signals efficiently. Additionally, the model includes a dynamic compressor that adjusts compression ratios based on the length of the visual context, ensuring computational efficiency. The training pipeline of Oryx follows a two-stage strategy, starting with text-image pre-training and followed by joint supervised fine-tuning with a mixture of image, video, and 3D data. This unified approach allows Oryx to generalize across different visual modalities and tasks. Figure 2 provides an overview of the Oryx architecture, which is designed to handle visual inputs of arbitrary spatial sizes and temporal lengths in an on-demand manner. The architecture offers two primary options for processing these inputs. The first option involves using a pre-trained Oryx ViT, which is equipped with variable-length self-attention. This allows the model to encode visual features while preserving the native aspect ratios and resolution of the inputs. The second option utilizes a dynamic compressor. This component offers on-demand compression on visual tokens, ensuring that the visual inputs are processed efficiently while maintaining a unified token form. These features collectively enable Oryx to adeptly manage a wide range of visual tasks and inputs, enhancing the functionality and versatility of MLLMs. The Oryx model has been evaluated on several general multimodal video understanding datasets, including VideoMME, NextQA, and MVBench. The results show that Oryx achieves superior performance, setting new state-of-the-art records. Notably, Oryx performs competitively with larger models, even those with 72B parameters. On the VideoMME benchmark with subtitles, Oryx achieves mean accuracies of 62.6 and 67.4. Additionally, Oryx outperforms previous state-of-the-art results on NextQA and perception tests by 3.3% and 4.5%, respectively. The model also performs well on GPT-eval benchmarks, with average scores of 1.49 on MMBench Video, 3.53 on Video ChatGPT, and 3.76 on Video Detailed Caption. These results demonstrate Oryx's capability to outperform advanced proprietary models like GPT-4v and Gemini 1.5 Pro on challenging benchmarks. To demonstrate the long context understanding capability of the Oryx model, experiments were conducted on benchmarks specifically designed for long video evaluation, including MLVU, Long Video Bench, and the Long Video subset of VideoMME. The Oryx 7B model surpasses all existing 7B model series on these long video benchmarks. The Oryx 34B model shows strong performance across larger models, achieving a mean accuracy improvement of 4.4% and 0.9% over previous state-of-the-art models with 72B parameters on MLVU and Long Video Bench, respectively. Notably, the Oryx 34B model outperforms GPT-4o on the challenging MLVU benchmark by 6.2%, highlighting its advanced capabilities in long video understanding. The Oryx model was evaluated on both image and 3D benchmarks to assess its spatial understanding capabilities. On image benchmarks such as MMBench, MMU, and DocVQA, the Oryx model maintains pioneering results, achieving an 84.5% mean accuracy on MMBench and a 91.4% accuracy on DocVQA. These results demonstrate the effectiveness of the method in comprehending images. In 3D spatial understanding, the Oryx model was tested on the ScanQA validation set, outperforming previous specialized models and general open-source MLLMs. These results underscore the robust adaptability of the Oryx model in addressing 3D spatial tasks, highlighting its versatility across various applications. An analysis of the effects of resolution and the Oryx architecture was conducted to illustrate the model's effectiveness. The experiments showed that native resolution consistently outperforms fixed sizes, with a more pronounced performance gap in text-relative benchmarks like DocVQA and OCRBench. Maintaining native resolution is a simple yet effective strategy for optimizing performance. In the ablation study on the Oryx architecture, Oryx ViT demonstrated superior alignment performance compared to SIGIL-IP. The dynamic compressor, compared to the MLP architecture, showed better fusion of multimodal data, especially with average pooling, which preserves the distribution of visual features without relying on complex parameters. Table 1 presents the results of experiments conducted on 4 multiple-choice benchmarks and 3 generation benchmarks to evaluate the general temporal understanding capabilities of video MLLMs. The benchmarks include VideoMME, NextQA, MVBench, and perception tests for multiple-choice tasks, and MMBench Video, Video ChatGPT, and Video Detailed Caption for generation tasks. The results show that Oryx achieves superior performance across a wide range of open-source video MLLMs, demonstrating its effectiveness in handling diverse and complex visual inputs. Specifically, Oryx outperforms other models in multiple-choice benchmarks and shows competitive results in generation benchmarks, establishing new state-of-the-art performance in general video understanding tasks. Table 2 presents the results of long-form temporal understanding tasks across 3 mainstream datasets, each with video inputs lasting tens of minutes. The Oryx model showcases superior performance, setting new state-of-the-art records and outperforming several proprietary models in various benchmarks. Notably, the Oryx 7B model surpasses all other 7B models in long video benchmarks, while the Oryx 34B model demonstrates significant improvements, achieving a mean accuracy enhancement of 4.4% and 0.9% over previous state-of-the-art models with 72B parameters. This highlights the Oryx model's remarkable capability in understanding and processing long-form video content. Figure 3 presents the results of the video needle in a haystack experiments, comparing the performance of Oryx 7B, right subfigure, with MLLM next video 7B, left subfigure, on the frame retrieval task. The results are displayed for varying inserted depths, ranging from 0.0 to 1.0, and across different numbers of frames, from 0.1K to 1.6K. The Oryx model shows superior performance in long-form understanding tasks, accurately retrieving relevant frames even when they are embedded within over 1K frames of irrelevant information. Table 3 presents the performance of the Oryx model on 6 representative image benchmarks, including general and task-specific tasks. The Oryx model demonstrates Tier 1 performance across a wide range of multimodal large language models, MLLMs. Notably, the model achieves an 84.5% mean accuracy on the MMBench benchmark and a 91.4% accuracy on the DocVQA benchmark. These results highlight the effectiveness of the Oryx model in image understanding tasks, showcasing its capabilities in both general and specific image-related tasks. Table 4 presents the performance of the Oryx model in 3D spatial understanding tasks using the ScanQA dataset. The table compares Oryx with various 3D-specific models and general open-source multimodal large language models, MLLMs. Key findings include Oryx's superior performance over specialized 3D models and its ability to surpass general MLLMs, indicating its robust adaptability and versatility in handling 3D spatial tasks. This highlights the potential of Oryx for extending its capabilities to more visual tasks and formats. Figure 4 illustrates the effects of resolution and resize strategies across various benchmarks. The left figure presents the performance across benchmarks using fixed size, native size, and larger images. The right figure displays the performance trends with varying resolutions, highlighting the effectiveness of native resolution. The text-relative benchmarks, such as DocVQA and OCRBench, show a greater sensitivity to resolution scale, while all benchmarks benefit from visual inputs with native resolution. This suggests that maintaining native resolution is a simple yet effective strategy for optimizing performance. Table 5 presents the results of ablation studies on the Oryx architecture, focusing on 2 core components, the visual encoder and the compression module. In Part A, the study compares Oryx ViT with the mainstream SIGLIP visual encoder, highlighting Oryx ViT's superior performance in aligning visual and textual data. The results show that Oryx ViT benefits significantly from processing visual inputs at their native resolution, outperforming the dynamic partition approach used by SIGLIP. Part B of the table evaluates the dynamic compression module against traditional MLP connectors, demonstrating that the dynamic compressor provides substantial performance gains by better integrating image and video data. Among various downsampling methods tested, average pooling emerged as the most effective, likely due to its ability to preserve feature distributions without relying on complex parameter training. The Oryx series introduced in this paper is designed to handle a variety of visual inputs across different tasks, temporal lengths, and resolutions in an on-demand manner. It serves as a unified multimodal framework for spatial-temporal understanding, incorporating innovative components such as Oryx ViT for native resolution processing, the dynamic compressor for efficient data compression, and a robust joint training strategy. Extensive evaluations show that the Oryx model achieves remarkable performance across numerous image, video, and 3D mainstream benchmarks. This work not only offers a new perspective on multimodal learning but also sets the stage for the development of more general multimodal large language models in future research. Thank you for watching.